It is time to start with the first example of a neural network. The network will exist of one neuron that has a single input and a single output. You might wonder what we can do with such a simple network. Well, here are some examples. A network with a single neuron can learn the relationship between the size of a house and its price, the amount of fertilizer and the health of your plants, or the relationship between the age of a car and the maintenance costs. All these examples model the relationship between one input and one output. But before I show you real-world examples like this, I will show you something that is even more simple. The relationship between x and y values. Look at the points in the diagram. Without doing any calculation, it is easy to see the relationship between x and y. For each x value in the diagram, the y value is doubled. This becomes even more clear when I draw a line through all the points. A line that tries to go through as many data points as possible is called a regression line. It is our goal to find the slope of the regression line. The slope of the regression line will play a huge role in our network, as you will see later. Just by looking at the diagram, we see that the slope of this line is 2. We can write this down as a function, y equals x times 2. This function will calculate the y value for each x value. Or, better said, it predicts the y value for any x value. The challenge is to find the correct value of the slope, 2. In a neural network, of course, the slope needs to be learned from training data. The algorithm to do this is called linear regression. And this is what our first network will use. So what do we have? We know there are 4 points on the line. Here you see their coordinates. We know that the values have some relationship that is determined by something called the slope. Our goal is to find the slope of the line. After finding the slope, we have a function that can compute any point by feeding it an x value. Perhaps you wonder why we need 4 points. 2 points should be enough to calculate a line function, right? That's true in this example, because all points fall exactly on the line. But very soon we will see data where the points will not fall exactly on the line, and at that point, the more data we have, the better the network can be trained. That's why we will use all data points to train the system. It's time to code. Let's make a network with one neuron, one input, and one output. Let me create a new Python file called firstnetwork.py. I start by defining the slope. A common variable name for the slope is w. The computer needs to calculate the slope for us, but we need to start with an arbitrary value. Now I create a function that takes an input and returns slope times input. You may not believe it, but this is already a neural network. I admit, it won't be able to predict very well, but nonetheless, we are well on our way. Let's make a prediction and feed the function with the value 2. The target value for 2 should be 4. Let's execute the code. As expected, the prediction is far off. What you just saw is called feed forward. The neuron took input value 2. The input was multiplied by w and produced output 0.2. This is a working example of a neural network with one neuron. It only has one problem. It is not very good at predicting. It needs to be trained. And this is where the training data comes in. Let's add it to the code. The data points are added, and now it's time to train the network. I will now make a prediction for all the inputs and put the results in variable pred. Pred now holds a list with predictions. The network now needs a way to express how accurate the predictions are. Each target value can be compared with a prediction. The difference between the two is known as the error of a single training sample. I'll create a list with errors for all samples. Then we calculate the average over all the errors. This average is called the cost. It is a single number that indicates how well the network is doing. Let's print the slope and the cost. Notice I am printing slope W and mark it as weight. For our purposes, weight and slope are the same thing. Let me execute the code. When we use weight 0.1, the cost is 4.75. You will get a good understanding of the meaning of this value soon. For now, let's just say the goal is to get the cost as close to zero as possible. That leaves us with a question. How can we make the cost go to zero? It turns out that this is not a trivial question, which we will see once our network will progress. For now, however, let's use the cost value to adjust the only parameter in the network that we control, the weight. I add the cost to the weight. Neural networks learn by repeatedly processing the training data. Let's put the whole thing in a loop to see what happens to the cost after 10 iterations. When I execute the code, the cost should go to zero. As you see, the cost values are all over the place. Let me plot them in a diagram for you. The diagram shows an oscillating pattern, and instead of decreasing the cost, it gets bigger with each iteration. Apparently, the adjustments are too big. To reduce the adjustments, we use something called a learning rate. Let me add it to the code. I'll set the learning rate to 0.01. This is just an arbitrary value to see what happens. I execute the code. Yes, that looks better. By taking small correction steps, the cost gets closer to zero. Now we need to find a good balance between the learning rate and iterations. I'll start by changing the iterations to 20. The cost keeps going down, but it is not close to zero. I'll make the learning rate 10 times larger. Look at the cost. With only 4 data points and 20 iterations, the network is trained. I bet if we increase the iterations just a bit, we get a perfect value for the weight. Very nice. Let me plot the cost for each iteration. This time, the error is gradually going down. Since weight adjustments depend on the cost, the updates are getting smaller as the cost gets nearer to zero. You have seen your first cost function. It is the mean sum of errors cost function. This function calculated the cost like this. There are 4 known targets. There are 4 predictions. Each prediction is subtracted from each target. This results in a list of 4 errors. The list of errors is averaged and out comes a single number. We repeated calculating the average cost 25 times and used it to adjust the weight. Since we only had 4 points in the data, this is no problem for Python. Even with 1,000 iterations, this will still be very fast to compute. But as our examples get more complicated, we will see that we eventually have to choose a different strategy. For now, we're doing fine. Updating the weight in the network is called backpropagation. Backpropagation takes the desired weight changes and propagates it back to the start of the network by adjusting the weights. Since our network only had a single weight, this was the only thing that was adjusted by the backpropagation. Later, this will get more complex. When the backpropagation completes, one training round is complete. The network is now ready to proceed with the next feed forward. So now that we have trained the network, how about making a prediction? Let's feed the network some test data it has not seen before and see how it is doing. I make a list of test predictions. And compare them with the test data. I execute the code. That is very accurate. There is nothing stopping you from training the network more to get an even better result, but I think this is already pretty good. Remember, our goal was not to create a perfect doubling function, but to create a neural network that makes good predictions. There is something I'd like to point your attention to. Look at the code. Each iteration, the predictions are calculated for all training samples. The cost is calculated by averaging the errors of all training samples. And at the end of each iteration, the weight is updated. I repeat, each iteration, all samples are processed and used to update the weight. This algorithm is called batch gradient descent. With batch gradient descent, every training sample from the training data is processed before updating the weight. You will see this algorithm often during this training. Later on in the training, we look at alternatives, but for now, this is what we will use to train the network. Look at this diagram again. It took our network 25 training iterations to minimize the error. We can improve this by using another cost function, and you will see how that works in the next part.